Let's do an example in relativistic kinematics. Okay, so supposing you have a photon coming along and it's going to bounce off a mass. So we have a mass m photon of wavelength lambda initial, and then afterwards you've got a photon bouncing off with some different wavelength, and you've got some mass, presumably also possibly moving with some momentum. Okay, let's find out what happens. So obviously we have to conserve energy and momentum here. So our energy momentum for the photon, well, if its initial momentum is pi, then its initial energy divided by c is just the magnitude of that pi, whereas the mass has no initial momentum because it starts off at rest, and so its rest energy divided by c is mc. And over here we have some different. Now if I'm going to put symbols on here, I should label them on the diagram. That's a really important point. So I'm going to have pi there, and I'm going to have a final momentum for this, pf, and I've also going to have momentum there, but I've already labeled that. So I've got pf, pf3 vector, and my energy momentum for this thing, it's got mass, so I have to be a little bit more careful and include the mass in the energy term. There we go. And conservation of energy momentum says that these two have to be equated. So we end up with a simple equation that conservation of energy is the first term, and then conservation of momentum is the second one. There we go. Which, as we can see, is just 4 equations, but we have 6 unknowns. We have this whole vector and this whole vector. But it turns out we can get some subset of information that is useful for an experiment by rearranging these two equations. So if we take that and simply rearrange, then we can substitute that into here. So p squared is just the dot product of p in itself. So I've introduced here the angle between the momentum here and the final momentum of the photon. And so now we can cancel terms that are identical, and we're left with. At this point, we recall that for a photon, the momentum is related to the wavelength in a very simple way. And we end up with a scattering formula that relates the wavelengths of the two photons to the scattering angle, and that's what Compton verified experimentally. As a side note, I'd like some kudos for managing to write H without putting a bar on it. Once I accidentally wrote, and then I had to buy a new birthday card. Anyway, this famous relativistic kinematics example was still fairly straightforward, and in fact you have to just follow those same procedures each time. Make sure you keep everything on the diagram, make sure you write down reasons for things I've been telling you, but you're going to have to write them down if you're telling somebody else without a video. And we can go through that process nice and easily in the future, but we do want to go on and talk about a microscopic theory, in particular the theory for electromagnetism. And in particular, we want to put it into tensor form, so it's really clear that it's Lorentz invariant. And for that, we need one final mathematical tool, which is tensor fields.